Our next speaker this evening will give us his perspective on this. Bob Armstrong, he directs the MIT's Energy Initiative, which links science, technology, and policy to transform the world energy systems. He is a chemical engineer, so he knows exactly what we're all made of. And he is a longtime Lexingtonian. Will you please put your hands together and welcome Bob Armstrong.
So as you just heard in the song, we're all made of carbon. I don't know so much about stardust, but I do know about carbon. The Earth has been recycling carbon since life began on the planet, and we're part of that carbon cycle. So carbon is not a problem. We owe ourselves to that, plants, animals, our food chain. But we do have a reliance on carbon that has developed dramatically over the centuries. In the mid-late 1700s, as the Industrial Revolution began, we started to depend more on carbon systems for our economic progress and well-being. First, we depended on wood and hydropower for powering machines to help replace manual and animal labor in producing goods and services. First with wood, as I mentioned in England, England used wood until basically they stripped England of all the trees, and then they turned to coal, which provided a more readily mined substitute. It was more energy dense and also more reliable in the sense that the water content and moisture was more reliable. And so coal started to replace wood quickly as a substitute for energy in powering machines. But later that got displaced by oil. Convenience of oil was evident, particularly in shipping and transportation applications. Gas later began to replace oil in many applications. So we see a series of energy transitions that take substantial time. Each of those energy transitions took about 70 years in time to make a transition from one major energy source to another. All of those resources, the wood, the coal, oil, gas, those were all plant-based, at least recently or in the distant past. And we're burning them, and presumably they'd recycle again. And so a question that comes to mind is, what could go wrong in that picture, right? And the answer is scale, right? It's something that I'd like you to take away from this, is that in early chemistry, chemical engineering, looking at fossil fuel combustion, you'll look at the products, the byproducts or end products of combusting those fossil fuels. What you get back are CO2 and water. And both CO2 and water are already in the atmosphere, so you say, what's the problem? And again, the problem is scale. If I could have the first slide, maybe it's up there already. Okay, here's the first slide, looks at the measurements of CO2 on top of Mauna Loa, going back to the late 50s, around 1960, is when NOAA got involved in those measurements. And you can see the steady increase in CO2 over time as we began to swamp the Earth's ability to recycle all of the CO2 that we were emitting associated with the growth of our global energy system. And you see the steady rise in that CO2 with an inset blown up to show you what's happened in very recent years. In particular, in 2016, we passed a somewhat dubious milestone of surpassing 400 parts per million of CO2 in the atmosphere over an entire year. And we continue to grow from that. In recent years, we've been between 410 and 415 parts per million. So what does that have to do with global warming? If you look at the climate science, the estimates of warming associated with increases in greenhouse gas concentrations in the atmosphere, 450 parts per million of CO2 equivalents is generally considered as the benchmark for a 2-degree rise in temperature, 2 degrees centigrade, relative to pre-industrial levels. Okay? As you can see, we're converging on 450 pretty soon, and if you take a printout of this and draw a straight line extrapolating the growth and intersect that with 450, you come up with about 2037 or 2038. So that's 17, 18 years from now. Compare that with 70 years for a typical energy transition, and you can see the time is now to get going and to get going really fast on this. That's 2 degrees. If you go back to the Paris Accord, the goal was 2 degrees or preferably something closer to 1.5. Well, 1.5 is nominally around 430 parts per million. That would be 7 or 8 years from now. So that would be an impossible thing to do, and we need to think not only about how we're going to address this emissions problem, but how do we get back ultimately as we go down the road. So that brings us in the next slide to the challenge that's in front of us, which is a dual energy climate challenge. It's dual in the sense that on the one hand, we expect a doubling of energy demand as we get out towards end of century, driven by the fact that population continues to grow globally, and the standard of living of the population we have continues to grow. That standard of living increase is important because people in developing countries are entitled to the kind of resources and quality of life that we have. But at the same time, the second part of this challenge is we have got to mitigate climate change by addressing the emissions problems we have. Right? And I'd like to stress the emissions part of that. I'm not going after carbon per se. It's that we emit CO2 from those processes that causes the problem with climate change. So if I can go on 2 slides, there we go. One of the challenges with addressing climate change, with mitigating climate change, is how embedded emissions are in our economy. The idea in this picture is to get you to think a little bit about where all these emissions come from. So as you look at this picture, try to identify places you see as emission sources. There's some easy ones in there, right? You see all the lights lit up. That requires electricity. So power is clearly one of those sectors that we've been focusing on for reducing emissions. You see, I think it's a taxi on the road there. So transportation is another area where we're clearly focused on reducing emissions. But there are emissions embedded in other places. You see a food store, or some people would call that a food store, where it does advertise salads there, so you can have a salad if you want. The food system we have consumes a lot of energy, and it emits a lot of CO2. We know that, and so that's another contributor buried in our economy and our lifestyles. The buildings that are there have embedded CO2. They're made of concrete and steel. There's emissions associated with those, or emissions associated with heating and cooling the building. So that picture captures the idea that throughout our economy, throughout our lives, we are consuming energy and there are associated CO2 emissions with that right now are too high, and we have to eliminate all of those. The next slide introduces an aspect of that emission system that I'd like to use as an example here, which is transportation. So I'm going to pull an example out of light-duty vehicles, so the kinds of cars that we drive, and what the emissions profiles are for those vehicles. And I'd like to look at what happens if you have different drivetrains. As you consider buying a car, what would be the emissions impact of different choices you might make? And particularly right now, since President's Day weekend is coming up, and that's a good car sales time, if you're thinking about buying a car, pay attention. All right, so we're going to look at 5 cars. We picked 5 cars here. These are, 2 of them are Toyotas, 3 of them are Hondas. And I'm not selling either one of those. I have no stock in a car company. We picked those because they all have about the same internal volume. They're roughly 115 cubic feet internal volume, so they're similar sized cars. The main difference across these vehicles is the drivetrain. The one on the far left is a Toyota Camry. It's the kind of car we used to have. It's a gasoline engine car. The other Toyota is a hybrid Toyota Camry. That's the kind of car that we drive now. Gets twice the mileage that the old spark ignition engine got. Then the Hondas cover a plug-in hybrid, a battery electric vehicle, and a hydrogen fuel cell vehicle. I don't know how many of you are shopping for hydrogen fuel cell vehicles. There are only 4 fueling stations in Massachusetts right now, so you might want to put that one off. Next slide looks at the emissions profiles, how we're going to rack up emissions on these vehicles. And I've just picked the one to show what the profile is going to be made up of. The vehicle on the far left we're going to be looking at is the hybrid, is the Toyota Camry that has a gasoline engine. So that's labeled here as an ICE. That's an internal combustion engine vehicle. There is a stacked bar that captures the emissions, and that's in 3 parts. The top part of that is the emissions you probably normally associate with driving. That is the emissions produced by burning the fuel to move you along down the road, or even just to sit still in a traffic jam. The middle block, the light blue block, is the emissions associated with making the fuel. Right? So the gasoline you burn has an emissions profile associated with that goes all the way back to drilling for oil, producing the oil, transporting the oil, refining the oil, distributing the oil to the pump, and then you put it in your vehicle. So there's an emissions associated with all of those steps. And then the last piece, the green piece at the bottom, is the emissions associated with actually making the vehicle. So there's steel in the vehicle, there's plastic, there's glass, there are electronics components. So lots of different things have to be made. Those all have carbon footprints associated with them. So the next slide shows the comparison of these vehicles. And there's a number on the top of each of these bars, which is the relative emissions in grams of CO2 equivalent per mile traveled relative to the hybrid vehicle. All right, so the hybrid vehicle's the second one from the left. That is the one on top. The spark ignition engine, the ICE gasoline engine, is about 1.37 times the emissions of that. What's interesting is if you look to the right, the plug-in hybrid and the hydrogen fuel cell vehicle have roughly the same emissions profile as the hybrid Camry vehicle. All right. The one that's best in this graph is the battery electric vehicle, and that is about 0.75, about 3/4 of the hybrid vehicle. Now, what may be interesting to you is that as you look over towards the far right, the 2 vehicles that you would expect to have no emissions do have emissions, right? So the battery electric vehicle and the hydrogen fuel cell vehicle have emissions, none associated with burning the fuel, right? If you use the electricity to drive your battery electric vehicle, there are no emissions there. But there were emissions to produce the fuel, the electricity. And how you produce that electricity makes a difference. What we've used in this picture is the US grid average carbon intensity for the grid. For the hydrogen fuel vehicle, you have to make the hydrogen fuel. What we assume there is that you do it the way we do most of the hydrogen production in the world today. That's steam methane reforming. You strip it off of methane, and you don't sequester the CO2. All right? And it's still about the same as a hybrid vehicle. So this last slide shows what's the impact of how you make the electricity. So this looks at the carbon intensity of the electric grid across the U.S. This is a fairly coarse picture. You can do this on a very local level if you want, but looks at the difference in carbon intensity across the U.S. and the impact of that on a battery electric vehicle relative to a hybrid electric vehicle. And you can see that there are parts of the country like the Northwest, which are highly dependent on hydropower for their electricity grid, very clean grid, so the battery electric vehicle looks very good compared to a hybrid electric vehicle. In a state like West Virginia that's very dependent on coal, you look worse than a hybrid electric vehicle, right? So where you are depends on what the choice is that you should make if you want to minimize emissions. I'd also like to say that in this slide that before we feel too good about being up in the Northeast where it's pretty green, Massachusetts is the worst electric grid intensity of all the New England states. I also like to say that I don't think this means we're better people than others. I think what this shows is something about the heterogeneous energy resources we have around the U.S. There's a lot of coal in West Virginia, so they use it. A lot of hydro resource in the Northwest, so it gets used. The same story plays out globally. What's available globally in different countries varies on where you are. And I think one of our big concerns as we race to address climate change is how do we deal with countries like India and China, which have vast coal resources? How do we help them to get to an energy system that meets the needs of their people, but doesn't emit anything like the carbon we have emitted over our history? The story also tells you something about some of the good news in the U.S. Although we sometimes think that we're not doing much to address climate change, in these different parts of the country, there are different experiments going on at the state and regional level to see how we can transform our energy systems. California has one, New York has a program, the New England states, RGGI, is one of the programs. So a lot of experiments going on that we think can inform us as we move, hopefully soon, to national and to global policy. The other thing I'd like to say that I think is hopeful for our future is that we have some very active young people and local people working to bring the urgency of climate change to our attention. I'd like to highlight two of the groups that we're focusing on here tonight and are partnering with us here. One is the Global Warming Action Coalition, the Lexington chapter, and the other is the Lexington chapter of the Sunrise Movement. So I'd like to acknowledge both of those groups. Thank you very much.